One of the biggest practical applications of calculus is the ability to optimize something given a set of conditions. So in this video, we're going to learn how to optimize something given a set of conditions. Hooray! I'll let you write that. Because it was so successful last time, we're going to do story time again. Hooray! Here's how it's going to work. My friend is a business owner, and his name is Blaze. Yeah, that's right. Blaze. Pretty awesome name for a business owner. Anyway, Blaze owns a can shop. He makes cans. You know, tin cans. Like that. And his boss tells him that, hey, Blaze, you gotta make me a can, and the can has to have a volume of 16 pi units cubed. And first off, it's got to be a right cylindrical can, so we're dealing with a cylinder. And because I'm lazy and I want the company to save money, see, we're trying to optimize something, we need to save money. So I need you to make the can that has the least amount of tin in it, so that I can get the most bang for my buck. Basically, I want the least amount of tin that still gets me 16 pi volume units. And so Blaze thinks to himself, he's like, well, I know that there are some wrong ways to do this. For example, if I make a tin that has a very small radius and a really long height, that will get me my my volume, right? Because my volume equation is V equals pi r squared h for a cylinder. So if I have a really small radius, then I have to have a huge height to compensate for that. But that's not going to be good for the amount of tin because, you know, like that surface area is going to be really big. Well, he also thinks to himself, well, I could go the completely other route and I could do a really big, like a pancake tin, and have a really big radius and a really small height. So like pi r squared each little h to get me my 16 pi. But that doesn't work also because you can see like this whole top, the tin has to have a top and a bottom. The whole top is going to be a huge surface area. And so it's like the Goldilocks problem. If my radius is too small over here, then I'm using too much tin. And if my radius is too big, I'm also using too much tin. But if you sort of think about it, like if I decrease the amount of tin I'm using and, I don't know, make a shape like this, then I can still get my volume. And so there's some radius value in the middle, somewhere in here, where the function of the amount of tin I'm using switches, and it like stops decreasing and starts to increase again. And so I'm looking for the point right here, which is just right for the amount of tin that I need to use. Hence the Goldilocks problem, because, you know, like porridge and stuff. Anyway, so Blaze thinks to himself, I have an idea. We use calculus. And he thinks to himself, well, the amount of tin that we're using is proportional to the surface area of the tin. So here's our tin. It's cylindrical. And the surface area, well, we have two circles on the top and bottom. So we have 2 pi r squared, because that's the, you know, surface area. And then we also have this like wrappy-aroundy thing. Okay, so if I look at a top view of this, I could imagine unrolling, like, I don't know, like toilet paper maybe. If you unroll the top and like take off the side, the length of it, if I take it completely off, the length of this would be the circumference, 2 pi r. Go ahead and convince yourself that if you wrap it around, you do get the circumference. And then the height of it is actually the height of the cylinder, because it's h, it's that length there. So we have 2 pi r squared from the two circles, and then we have a rectangular shape. It's 2 pi r times the height. Sweet. Blaze thinks, well, that's a pretty good start. Now I just need to optimize this, except we have a problem. And the problem is that r is a variable, but h is also a variable. And he doesn't want to do any nasty product rules or anything like that. So we're going to try to skip that nasty step. And so he thinks to himself, is there a way that I could get r or h in another equation together? And he's like, I have it. Remember that my boss told me, Blaze's boss told him, that the volume had to be 16 pi. Well, the volume of a cylinder is pi r squared h. Oh. Well, the volume needs to be 16 pi. The volume here is not a variable. It's a constant. It's 16 pi. But this gives us a relationship where we have r and h in an equation related to each other, and so this allows me to solve for one of them. So in this case, h is going to be easier to solve for because it's just h. So we're going to solve for h. H is going to be 16 pi divided by pi r squared. I divided because of algebra. Okay, and now the pi's go away. Nah. And so h is just 16 over r squared. Very nice. So I'm going to take this 16 over r squared and plug it into h in our equation. So we're going to get s equals 2 pi r squared plus 2 pi r times 16 over r squared. And so this formula right here, this formula, the graph of this is this, right? This is the equation that we just had, 2 pi r squared plus pi r times 16 over r squared. There's a 2 here. Yeah, okay. And if you were to graph this on your calculator, it would look something sort of like this. There would be some minimum that we're looking for. But this is calculus. How do we find minimums? We don't use graphs. No, we use calculus. So what we're going to do is we're going to do the first derivative test on this thing, basically. We need to find this point. Tangent line. Probably going to be horizontal. Tangent line is like slope. We're going to look where the derivative is equal to 0. So it's easy. We take this, and we're going to take the derivative. Let's do it. S prime equals stuff 4 pi r. And then if we simplify that other term, let's do that first, because I don't want to use the product or quotient rule. So let's simplify the r's, because one of them is going to cancel. We'll get 2 pi, and actually 2 times 16 is 32 pi, divided by r. And to do this derivative, I could bring the r up to the top and write it as r to the negative 1. And let's take the derivative of that. So I bring down the negative 1, I have negative 32 pi r to the negative 2, but remember that r to the negative 2 is basically divided by r squared. We don't really like negative exponents. Okay, and notice that there's no dr dt or dr dx or anything like that because we took the derivative with respect to r, because that was the variable. There's no time element in this problem. Alright, and now let's think about it. If we were to find the critical values, well, one of them is obviously r equals 0, because it makes that sad in the bottom. But let's think about this realistically, and that's the nice thing about optimization problems. If we got a negative value for r, like negative 8, does that make sense in the problem? No, because you can't have a negative radius. Just like here, r equals 0 doesn't make sense because you can't have a 0 radius and have a positive volume, or any volume, because you don't have a cylinder if the radius is 0. So what we need to do is basically just solve the rest of it for r. So we're going to set s prime equal to 0 because that was our thing to find critical numbers. So we're going to do 4 pi r minus 32 pi over r squared. Good way to do this is just multiply everything by the r squared to get rid of it. So r squared, 0 times r squared is still 0. 4 pi r squared times r squared is 4 pi r cubed. And then here, that'll cancel. So that turns out to be nice. So minus 32 pi. There we go. And we're almost done, basically. So we do 4 pi r cubed equals 32 pi. Notice that the pi's are going to cancel. And if I divide both sides by 4, I get r cubed equals 8. So r equals 2. Ta-da! And this is, in fact, the Goldilocks number. R equals 2 gives me the minimum surface area for my tin. Let's also figure out the height. Well, to figure out the height, we had the relationship that the height was 16 pi over pi r squared from the first part of it. And we just found out that r equals 2. So all I'm going to do is just plug in r equals 2. And I get Remember, pi's cancel. Great. I get 16 over 4, and so the height that minimizes this is 4. And so if I draw the cylinder, it turns out to be a pretty geometrically nice cylinder because the height is 4, and the radius is 2, which means that the total diameter is 4. So it's sort of like a square cylinder if you want to think about it that way. And in the end, Blaze takes his idea to his boss, and he's like, yo, boss, guess what? H is 4, and R is 2. And his boss is like, awesome, here's some money. Yay! I'm going to do another quick example, less applicable, but still good to know how to do, just in terms of AP style problems. Let's say we have the curve 2y equals x squared. If I see this, I can solve for y right away, so we're going to do it. Y equals x squared over 2. It's a parabola. Looks something like that. And what I'm going to do is I'm going to take a point, and I'm going to take the point 4, 1, which is here. And the question is, label it 4, 1, and the question is, what is the point on the graph of this such that the distance from 4, 1 to that point is the smallest? What a weird question. Well, let's do it. Let's call this point x, y, and how do I find distance between 2 points? I use the distance formula. So d squared equals x minus 4 squared plus y minus 1 squared. And then remember that if we're going to do optimization, I need d in terms of one variable. Well, I have x, I need to find y. Do I have a relationship between x and y? You bet your bottom. It's right there. So I'm going to plug it in. D squared equals x minus 4 squared plus x squared over 2 minus 1 squared. So that's my relationship there, so I'm going to plug that in. And now I could take the derivative. Notice you could take the square root first, but it'll turn out that it won't matter, and it's a lot easier to not take the square root first. So in this case, I'm taking the derivative with respect to x, because that's my variable. So I do 2d, dt, dt, that's fun to say. And now here I need to use the power rule, so x minus 4 to the first, and a chain rule, 1. Okay, plus, same thing, bring down the 2 stuff to the first, and the stuff is going to be the same, so it's x squared over 2 minus 1, but you have to chain rule it, and the chain rule is going to be 2x over 2, which is just x. Excellent. Let's go ahead and simplify the right-hand side of the equation. So we have 2d dt equals, if I distribute all of that, I just get 2x minus 8. And if I distribute all of this, I'll get plus, well, I have 2 and x times x squared over 2 is going to be x cubed. And then I have a minus 1 times 2 and x is a minus 2x. And so this actually simplifies very nicely. The 2x's cancel, and I'm basically left with this equation. 2d equals x cubed, no, I'm not done yet, 2d dt, that's important. 2d dt equals x cubed minus 8. Okay? And now remember that I'm looking for where d dt equals 0 because I'm doing my first derivative test. Well, the distance itself could never equal 0 because clearly the point 4, 1 is not on the curve. Okay? So what I'm going to do is I'm going to make this equal to 0. So let's do it. X cubed equals 8, so x equals 2. Hooray! X equals 2, and let's plug in, and that's my only solution here, and I know that it's the right solution because in context there cannot be, first of all, there can't be a maximum distance because clearly, like, if that's my distance, this distance over here is longer. So the distance at 2, whatever, is the shortest distance. Let's find the y value. Well, y was x squared over 2. And if I do this, well, I'm going to get y equals 2. So the point that's closest to 4, 1 is going to be 2, 2. And that's it.